Two trains are traveling on parallel tracks in the same direction. One train travels at 130 miles per hour. Another train travels at 100 miles per hour in the same direction. At 2 o'clock, the faster train is 10 miles behind the slower one. Here's the question. What time does 5G get there? You thought I was going to ask something else, didn't you? Yes, it's true that we're all on the bullet train to 5G right now, but at times, doesn't it kind of feel like we're really on that zoo train that only goes in a big circle? Wait, that might just be me. Hi there, I'm Amelia Dalton, host of Chalk Talk. All aboard the 5G Express. Today, the engineer at the controls is Ken Karnofsky from MathWorks. Today's stops will include, but will not be limited to, modeling, simulating, RF power amplifier, linearization, and hybrid beamforming for massive MIMO. Oh yes, it's cool. Ken and I are about to leave the station and talk about designing 5G wireless technologies with MATLAB and Simulink. Are you on board? And before we get started, don't forget to click that link. There you can find more information about designing 5G wireless technologies with MATLAB and Simulink. Hi, Ken. Thank you so much for joining me.
Hi, Amelia. How are you?
I'm great. Thank you for asking. So it seems like engineers these days, for just about every application or system, are saying, oh, but 5G will change all of this that we're doing today. Now, that seems like a lot of expectation to put on 5G technology. Ken, what do you see are the real underlying goals of 5G?
Okay, well, the goals are really to achieve and implement technology to handle much faster connections.
Sure.
For applications such as 4K video and virtual reality, low latency and very reliable connections for safety critical applications such as connecting vehicles and autonomous or otherwise.
Sure.
And the third is for the Internet of Things. As more and more devices get connected to the network, it has to be able to handle that scale of connectivity.
Right.
So if there are millions more devices or billions more devices than there are today, the network has to be able to handle that.
Absolutely.
Right.
Okay, so the whole main point of this is higher data rates for everybody, right? So Ken, what's all involved in that?
Well, first of all, the main point in the initial release is higher data rates. In the subsequent releases, it will also be lower latency, which means respond immediately.
Sure.
And this massive connectivity of devices. So what's involved in that is to get higher data rates, you need more bandwidth. Just, communications theory tells you need more bandwidth
right.
to do that. And the current technologies aren't as efficient as they could be in using the spectrum that is available. Sometimes people talk about a spectrum shortage. And it's not necessarily that there isn't enough spectrum, that it's just not being used efficiently.
Right.
And there are other technologies. So getting back to the higher bandwidth, the main way that that's happening is to go to higher frequency bands. If you operate at a higher frequency, the bandwidth can increase correspondingly, and you can transmit more data over that.
Sure.
The problem with that, or the challenge with that, is that the physics changes. The way signals propagate through the air is different.
Sure.
And all of the underlying electronics to operate at those very high speeds and bandwidths need to operate differently. So that's why there's a need for a new physical layer. There's a greater integration between the RF and digital front end, so different architectures there. And then at a low frequency, the signals can travel a long distance. And the higher frequency you get, then they fade at a very short distance. And the innovation is that they've come up with ways to use what's called massive MIMO. Lots and lots of antennas where you can steer the beam and the signal and concentrate it in a specific direction. And that's the way you can overcome the losses that happen at these higher frequencies.
Okay, so every part of what you just described is a huge engineering challenge, and getting them all to work together seems like yet another massive challenge.
Yes, each area individually is a massive challenge, and the whole thing is an even bigger challenge.
Yeah.
And it's really putting strain on engineers for a couple of different reasons. One is that engineers are often, once they get past their undergrad level, they specialize in a particular area.
Sure.
And companies that make tools and equipment for them tend to cater to those particular engineers.
Sure.
And now what's needed is a way to bring those disciplines together. And we call that multi-domain engineering. So where each engineering domain can work in the way that they want to, but that contribute to a model that gives you a representation of the overall system.
Nice. Okay.
Otherwise, if you don't do that, then you have to wait till you get to the lab and you've actually built hardware in a prototype.
Right.
That's a long time, and it's very expensive to fix problems at that point.
Absolutely.
So if you can find a way to get the engineers to understand what they're doing together and be able to simulate that, that can be much more effective. And there are different components to that. One is everybody needs a waveform or a signal to test whatever they're doing, and they have to be confident that it conforms to the standard. That's number one. Second is that the signal processing, we talked about a new physical layer that really boils down to a new DSP techniques to handle these large bandwidth signal processing tasks. The channels and the interference, I talked about the physics being different. Mm-hmm. That means that you have to model that. If you want to do a realistic simulation and work out the problems before you get to the lab, then you need a good model of what's going on with the signal when it gets transmitted over the air.
Sure.
So there's channel models and interference between different signals. The RF front end is changing. Those designs have more and more digital content. Antenna arrays, I talked about massive MIMO. The design of that is another challenge. And then the beamforming that happens, there's a choice of how much is done in the digital domain and how much is done in the analog or RF domain. A system architect needs to put all of these things together to characterize if a change happens in any one of these subsystems, how does that affect the overall performance?
Okay, so there's going to be a lot of modeling and simulation required to get 5G ready and off the ground. But Ken, how exactly is that going to happen?
Well, that's a multifaceted question with
right?
multiple answers. We'll get to these over the next few minutes.
Yeah.
But the first part is that engineers don't want to have to kind of design the test waveforms themselves. So
sure.
The standard is specified in this big, long document, hundreds or thousands of pages. And what they don't want to do is read all those documents and then write code to generate the waveform.
Sure.
So typically you would get those waveforms with test equipment, but if you want to do it in a simulation and do this multi-domain engineering, you need a waveform that can work in that environment.
Sure.
MathWorks offers a range of signals. We support exploration of these new 5G radio techniques, but we also have the existing 3GPP standards based on LTE, as well as 802.11, which is wireless LAN. And all of these operate in similar frequency ranges, so it's often convenient that if somebody's doing something in 5G, they have to make sure that there's interest in understanding the coexistence between these different standards.
Sure.
So if you're focusing on 5G and you need to understand how that's going to coexist with a wireless LAN signal, it's helpful just to have an off-the-shelf wireless LAN signal to help you do that.
Absolutely.
Yep.
Okay, so I've been hearing about this new 5G NR physical layer. What's going on with that?
Well, NR, first of all, stands for new radio. That's just what the 3GP people and the people working on this standard have said. This is different from what's in LTE, so it's new.
Okay.
And the radio is just the part of where the digital world meets the analog and RF world and meets the real world. Right?
Okay,
so
sure.
It's not the core network where things are getting routed over the internet. It's really the interface between the electronics and the environment, the channel. So the physical layer, again, to achieve these high speed, the terminology is enhanced mobile broadband, getting these higher bandwidths. They had to come up with new techniques to accomplish that.
Sure.
There are kind of three main categories of this. One is the kind of the frame structure, the way you take the bits and pack them into something that you can transmit over the air. That needs more flexibility. There is something called channel coding, which is the way that the signal is encoded so that it can deal with any interference that happens on the way from point A to point B. And then the modeling of that environment is also required. And so these things are all being specified in the 5G standard. And so to have a 5G waveform and to design the physical layer, if you want to design a transmitter that conforms to the standard, you have to deal with all of these new technologies.
Okay, so Ken, walk me through some of the signal processing aspects.
Okay. One aspect of the DSP is being able to take advantage of the larger available bandwidth. 5G, the Release 15 standard, is going to use the same basic waveform as LTE, but there's some enhancements that are being made to improve the capacity. One is something called flexible subcarrier spacing. So if you can increase the spacing, that increases the bandwidth that's available and also gives you a shorter latency as well. So in LTE, there was just a fixed spacing. It was 15 kilohertz. And in 5G provides 6 different options, and each one has a different bandwidth and latency characteristic. It gives flexibility to the designer to be able to take advantage if conditions permit. you can get potentially up to 8 times the bandwidth that you have in LTE. However, that adds complexity to the design, so you have to be able to incorporate that and simulate it.
Sure.
The second area is for making more efficient use of the spectrum. There are techniques that fall into the category of spectral shaping, filtering, or windowing, and this ensures that the signal is concentrated in the specified band and don't link into the adjacent bands where they can cause interference or problems with other transmissions.
Now, what about channel coding?
So 5G introduces 2 new channel coding methods, and the purpose of this is to improve the error correction capability and then the channel capacity of the signal as well. And this is all geared towards having higher data rates. If you don't have to spend time correcting for error, the more the processing is dedicated towards actually transmitting the signal, therefore faster data rates. So the 2 techniques, they're different techniques for the data channel and the control channel. For the data channel is LDPC, low density parity check, and that's a memoryless block coding scheme. It's known to be very efficient, but it's computationally complex. So there are challenges with the hardware implementation of this technique, although it's known to be kind of optimal in many regards.
Okay.
And then polar codes are better suited to the control channel, which has to do with the protocol checking. Unlike the turbo codes, which were used in LTE, these can really fully achieve the channel capacity.
What do we do to see how 5G is going to perform in the real RF environment out there? It's not going to exist by itself, and there's still LTE and a whole bunch of other stuff going on.
That's absolutely right. And one way of doing that, again, with the goal in mind of being able to simulate the system before you get into the lab or into field testing, you need to be able to model the channel and any sources of interference. One of the sources of interference is just other signals that are out there in the world coming from existing LTE signals. People aren't going to throw away their LTE phones once 5G comes along, not right away anyway.
Right.
There are all kinds of Wi-Fi devices happening, and so if you do bring in a 5G device into your local coffee shop, there's still going to be Wi-Fi going on in that coffee shop. And
right.
You have to be able to deal with that, right? The second is propagation channels. So we found that, again, because of these higher frequencies where 5G operates, we need more sophisticated methods for modeling the way those propagations happen. And MathWorks is supporting this along with models that we have for today's standards, LTE and wireless LAN, as well as customizations that an engineer might want to make. And then finally, another big concern is being able to determine, where do I actually put my base station?
Right.
Is it going to interfere with another base station? Am I going to have the right signal coverage? There's a measurement called SINR, which is signal to interference plus noise. And those are all measurements that engineers use to determine whether they get the coverage and whether the transmitter is going to be able to send the signal to the receiver and the receiver is going to be able to properly accept that signal. So MathWorks is addressing this by supporting the channel modeling. And we also have new capabilities where you can visualize the location of transmitters and receivers and the coverage and SINR on a map. So you can grab a street map, say my transmitters and receivers are here, and actually see how things are going. And so people who are the device makers find this useful, but also the cellular carriers also care about this because it helps them with off-site planning and where they're going to put their infrastructure.
Sure.
Along the same lines, 5G, as in previous standards, there's actually a specification in the standard of what needs to be modeled in the channel. And so it's this big long thing, 3GPP TR 38.901. And there are a couple of things that are different about this from LTE. One is the range of frequencies that are supported. So it goes all the way up to the very high millimeter wave frequencies that 5G is going to operate at.
Nice.
There are a couple of techniques, both of which MathWorks has implemented in our 5G library. One is the full 3D model. So if you need complete fidelity, you would use this technique. If you want to get an approximation but have more efficient computation or simulation, you can use another variation called the tap delay line model. So it's an approximation, and sometimes you just want to get a first cut answer fast. Sure. And once you've got things right in the right ballpark, then you do the more accurate simulation. The standard and our implementation specify a number of key control parameters that are important to designers.
Okay, so Ken, is there a way to model and simulate the overall link performance with various approaches?
Yes, absolutely. This is something that engineers who are working on the physical layer or the system engineers have been doing since the beginning of wireless engineering, but there are ways to make it easier. And what we're finding is that most people who have been working on 5G up till now will start with an LTE baseline and then put in the parts that are being considered or who have been standardized for 5G.
Okay.
So we're providing a framework or an end-to-end reference model that has all the elements in that processing chain so that a company that might be considering a specific design or developing their own IP can develop that in MATLAB and then plug that into the reference framework that we have and see how that affects the overall performance. Or you might want to go from something that's in kind of a high-level model just to see, this is my specification.
Right.
And then you want to do a more detailed design, which is going to reflect the implementation. You want to see, okay, am I still getting the same results when I made this design choice in my implementation? Again, you can plug that back into the reference model and get the same plots and charts and performance metrics.
All right. So, Ken, looking at the RF amplifier stage, we used to be able to keep the RF and digital parts of our design pretty segregated, but 5G is forcing us to work with both domains together, right?
Yes, that's right. And this was already happening as we see RF transceiver chips and devices having more and more digital content in order to achieve higher power or operate at larger bandwidths, get more linear performance. All of this requires DSP or digital control techniques, as well as the RF and analog technologies.
Yeah.
And this has the potential to bring the cost down and improve the performance of these more integrated technologies. So these issues are all kind of present in the design of an RF power amplifier. So for 5G, these power amplifiers have to be highly efficient. But to be efficient, what happens is that the behavior becomes nonlinear.
Ah, okay.
And what you can see that in this plot over here, that if you have an input stimulus, the ideal is that the output should be linear or just directly proportional to that input. But what happens because of the very efficient high power operation, you see that it becomes nonlinear. It's an effect called compression happens, and you stray from that linear operating point. And there are also memory effects, which means that the current output depends on previous inputs.
Oh, okay.
So that makes things quite complicated. To compensate for that, clever engineers have come up with a technique called DPD, and there's kind of a family of techniques for what's called linearization,
Okay.
which means you want to straighten out that curve so it does become linear. So you can actually get away with a more cost-effective but very high power, high efficiency amplifier, and then deal with the linearity issues with a smart DSP algorithm called digital pre-distortion.
Okay, so where do we start? It seems like we can't just pull a model out of thin air.
That's right. The way this is traditionally done is a manufacturer will have an RF power amplifier device, a chip or a board, and then you go into the lab and you implement something on an FPGA and test it out and see if you can make it linear.
Sure.
Right. Okay, that's fine if you have the chip. It's also is time consuming because you got to write all the HDL code to get it implemented on the FPGA.
Sure.
What happens when you don't have the chip yet? You can extract a model either from simulations, if you've got a circuit simulation of the device, but it hasn't been manufactured yet, or if you actually have the device, you can take data that represents the behavior of that power amplifier. And then we've recently introduced the capability to fit that model in MATLAB so that you now have a model of the power amplifier.
Nice.
This is an iterative process. Very rarely get it right the first time.
Sure.
And so until now, the techniques for doing this have been what I would characterize as a black box approach, where you can kind of get a model, but you don't really understand what it's doing and you
Sure.
can't change it.
Yeah.
Right now you have open white box MATLAB code. And if you can read this 20 lines of MATLAB code, you can change it and make it do what you want and make adjustments until you have a model that makes sense to you and has the accuracy that you're looking for. Once you've done that, then what do you do with that model? So you could create a power amplifier model block that can go into our Simulink environment where you can simulate that power amplifier together with the DPD algorithm, and you get a complete closed loop simulation of the whole thing. An accurate model of the real device data, and then you can go to town developing your algorithm to compensate for whatever nonlinearities you find.
All right, so how can we simulate the RF power amplifier along with the DSP behind it?
Okay, so what you need is a simulation environment where you can actually simulate both digital and analog or RF together in the same environment.
Yeah.
And also close the loop.
Sure.
Because the DPD is an adaptive algorithm, which means I can interpret this diagram a little bit. The output of the DPD, the top branch, is going from left to right, and the signal is feeding into the power amplifier. And then there's a feedback loop where you can see how well it's doing, essentially. And what's called the error signal can help you adapt or adjust the coefficients of the DPD algorithm.
Sure. Okay.
And then you keep doing it so that you stay kind of locked into the characteristic or the behavior that you want. So this is a familiar technique. If you look at RF or analog simulators, this happens all the time, or pure digital techniques, you can do this. But it's a unique capability to be able to do the DPD and power amplifier together in the same environment. And the other thing is that typically the circuit simulators where power amplifiers are designed, it can take days of simulation for a few seconds of real time. So we can speed those days up to minutes, hours at most, basically going down dramatically so that you can really go through and fine-tune the algorithm and iterate much more quickly than you would with conventional techniques.
Nice. Okay, so Ken, you said earlier 5G takes advantage of massive MIMO. That seems like a massive headache to model and simulate. How do we approach that?
Yes, it does seem to be a massive headache from the response we're getting from customers who is, as soon as they know that we have some capabilities to help them address that, it always gets their attention.
Yeah.
They kind of sit right up and pay attention when one of our field engineers is telling them about this technology. One of the reasons it is a headache is that this is another multi-domain problem.
Sure.
So you have to be able to design antennas, and to do the antenna arrays and model the effects between lots of antennas working together. And then to do the beamforming, you need to be able to span both the analog and digital domains as well. So you have antenna design, RF and analog design, and digital design. Again, traditionally, those are different domains, different types of tools. You need to bring those all together so that you can actually get a sense and a design that's going to work. There are important trade-offs to be made here. One is that if you have a very narrow beam, I mentioned that millimeter wave signals fade very quickly.
Yeah.
So you want a narrow beam to try to concentrate the signal and get a better, what's called gain, be able to get that signal to travel farther. But you don't want it to go too far because there are other considerations in terms of the capacity of your channel where you want a less fine point beam.
Sure.
So you got to make trade-offs there. And then there are also cost trade-offs as well in terms of how much you do in analog and how much you do in digital, and that can affect the cost of your implementation.
Sure. Okay. And the main thing we're trying to do with all this MIMO is beamforming.
That's right. And this is where this cost architecture trade-off comes into play. The idea with these large antenna arrays and beamforming is that you can have a great deal of flexibility about where you can steer the beam when you have multiple users in the environment. And the most flexibility comes with an all-digital implementation. But the problem with that is that that's going to drive up your cost.
Oh, okay.
So what is being explored and what looks like an attractive solution is to have a combination of beamforming in the digital domain and the RF domain, where you have somewhat less flexibility, but you can lower the cost of the implementation. In many cases, that looks like that's a trade-off that's worth making.
Sure.
But again, you have to explore and iterate to find the design that's going to be right for the specific product that you're building and the scenarios where it needs to operate.
Definitely. Okay, so you said earlier we were going to talk about connecting cars with 5G.
That's right. Although we're not quite doing it with 5G today, or even even in Release 15. As I said before, Release 15 is focused on the very high-speed mobile broadband case, but it's still within the vision in 5G for the future. So in the meantime, there are actually two competing approaches for connecting cars. One is based on the wireless LAN or Wi-Fi technology, and the other is based on cellular technology. So the cellular one, which is called cellular V2X, CV2X, is specified in the previous version of the 3GPP standard, which is the last LTE standard, Release 14. We support that in our LTE system toolbox. In that case, the vehicles can communicate with each other directly, or they can also communicate over the network as well. Okay. And so there are trade-offs between how quickly do you need to respond versus do you need to provide visibility into what's happening further down the road in traffic. Many people are looking at that, and that seems very promising, and that will evolve into the 5G V2X solution over time.
Gotcha. Okay.
but not yet. The second technology is based on a Wi-Fi or wireless LAN technology in the 802.11 standard, and it's called DSRC, which stands for Dedicated Short Range Communications. And this has very nice low latency characteristics. It's great for direct communication between the vehicles, but doesn't have the ability to communicate over the network infrastructure for other types of applications. Although it is being mandated in some countries, and you'll start seeing this in some vehicles in some parts of the world over the next couple of years.
Okay. Now, does 5G have an IoT story as well? It seems like all that bandwidth and spectral efficiency could come in handy for IoT.
Yes, all that bandwidth and efficiency will come in handy as the number of IoT devices increases. But again, like the V2X case, the initial 5G standard really isn't being designed for the IoT connectivity case. So again, if you want to connect an IoT device over a cellular network, there are actually specifications in the LTE standard for doing that. The one that's now getting a lot of interest and designs are going on now is called NB-IoT, for narrowband IoT. It's actually the opposite of high bandwidth. It's actually saying I need a device that's going to operate with one antenna and a battery that's going to last for a long time.
Right.
So I don't need a lot of bandwidth. I just need to transmit little data over every once in a while. My meter needs to send the signal to the electricity provider or something like that. Right? So it's not a lot of data. There are different considerations. Lower cost and power, greater range is just a different flavor of LTE. But it's compatible with the LTE network. There are actually lots of other standards for IoT devices for local area networks or personal area networks. So Wi-Fi and Bluetooth and other devices are all part of the IoT picture. The NB-IoT, the way this is different from the general LTE is that it has a number of techniques to reduce the cost and power so that a consumer device that costs in the tens of dollars can have a low power and inexpensive part that goes into it.
Okay, so let's put this all together into a design flow. How do we take advantage of MATLAB and Simulink in our 5G designs?
Well, there's actually a range of ways to do that. Many customers are already using MATLAB to do their initial simulations and design of their algorithms, but we see advanced customers are taking that much further. And we see this example from Huawei. The head of their algorithm and architecture design group is recognizing that MathWorks offers a solution for multi-domain simulation that I talked about earlier, and then prototyping and verification to get something from a concept into prototypes and then implementation in hardware. What are customers like Huawei and others doing? Well, they're starting with a design environment. We talked about this multi-domain engineering.
Yeah.
And MATLAB and Simulink provide that capability. It's being able to have tools, a platform where you can simulate all these elements together and then work in the environment that makes the most sense. So people who are doing the waveforms and measurements and algorithms tend to gravitate towards using MATLAB because the language is very well suited to doing that type of task.
Yeah.
Very efficient. Somebody can get from an idea to a working algorithm or even a patent in a couple of days.
Nice.
Right. But when you're doing the full system or the other parts of the system, that's where Simulink comes into play, where digital meets analog. And you can also start modeling with a higher fidelity when you want to go from the simulation to something that can be implemented in hardware.
Sure.
So we provide a range of tools that cover the full link path from the waveforms to the RF front end, antenna design, modeling channels, and then the mixed signal that connects the RF and digital.
Okay, so can we integrate this with actual hardware in our testing loop?
Yes, so we support over-the-air testing with a range of hardware. And again, this is a rather unique capability. The testing is often done by buying some test equipment and then using the software that comes with that test equipment.
Right.
Our approach is somewhat different, where the same waveforms and tests that you perform in simulation can be applied to over-the-air testing with hardware. You can connect a software-defined radio device at relatively low cost, put it on your desk or in the lab to get some initial calibration of your design to determine whether you can really transmit a signal that complies with the standard or whether you can receive one. And then later on, when you're actually moving into full design verification, you want to move into the kind of the high-end test equipment that's provided by test and measurement vendors. We have an instrument control toolbox that connects to those. And again, the same signal can be used to test your simulation, work with a low-cost SDR platform, or with any commercially available RF test instrument.
Nice. Okay. So, Ken, what about performance of these simulations?
Yes.
Seems like this could require a lot of computation.
It does require a lot of computation. And so some of the algorithms themselves are quite computationally intensive.
Yeah.
And then you want to run many simulations over a range of parameters. And to calculate the error rates in your link simulation can be very time consuming.
Yeah.
So the way that we handle that is we provide a range of parallel computing tools that scale up from the desktop, where you can run these simulations on your multi-core desktop machine. And then you can take advantage of GPU devices as well to speed up certain algorithms. And then you can go up to a cluster or cloud services for very large-scale simulations as well.
Nice.
And we have customers who are doing this on a regular basis because they need to get this work done in as short a time as possible.
Right. All right, Ken, this has been a lot to take in today. Let's go over some of your main points.
Okay, so to summarize, 5G design is very complex. It spans multiple engineering domains, and it's requiring engineers to model and design new kinds of algorithms and implement those in hardware and software.
Sure.
So what MathWorks provides is a capability which allows very rapid and efficient algorithm design and verification of those algorithms with simulation. It spans the RF and digital and antenna domains so that you can simulate all of those together and model the interactions and get an optimal design. You can use the same models to do over-the-air tests or to verify your hardware or software implementation. Then you can also use our code generation technology to take any new algorithm that you have and refine that and get that implemented on a hardware device and test that out in a prototype, and then ultimately move that into production.
Excellent. So one last thing, where should my audience go for more information?
Well, I think the best place to start would be to go to mathworks.com, download this 5G ebook, which gives an overview of many of these technologies that I discussed today in a bit more depth, with links to additional in-depth resources as well. So I think that would be a great place to start.
Excellent. Well, I will click that link right now, and I think that's all I have time for today. Thank you so much for joining me, Ken.
Thank you, Amelia. It's been a pleasure.
And before we go, you didn't forget to click that link, did you? There you can find more information about designing 5G wireless technologies with MATLAB and Simulink from MathWorks. For Chalk Talks, I'm Amelia Dalton from eejournal.com. For more Chalk Talks, head on over to the Chalk Talks section of EE Journal or check out YouTube, keyword EE Journal.